Hello friends. So in this video we discuss about four approaches in tree to returning from leaf to root. So this is topic basically of advanced data structure, and this topic related video is not available right now in the YouTube. So this is the first video of this topic on YouTube. PDF of this topic is I have put it in description box as a drive link to check them. So first approach is using a stack. So in this approach, we traversing from root to leaf, and every step of traversing, we put the nodes in the stack. So how this implementation is done? Let's take one example. So in this tree, we are at this first root 2, and we need to traverse from this root 2 to this leaf 2. So first we are at this root 2, so we put this root 2 in this stack, and from in traverser we come here 7 and put also 7 in the stack, and then we come this leaf 2. Now we need to return to root, then we first pop out this 7 and we come to this 7 node, then we pop out again, then we come to this root. So this is the basic approach of the stack. Now let's see the properties of this approach. So here in this approach we don't need any additional information in tree structure, because we using stack as an external memory. So we don't need any additional memory from returning leaf to root. And here the maximum size of the stack dependent of the number of nodes in the tree. So basically the if tree is uh, balance, then we need maximum 200 items at max. This is the average as a standard. So this is the properties of the stack, and this stack is basically used in our recursive implementation, where we when we search using recursion, then computer memory use this stack approach. So our next approach is the back pointer. So it is easiest approach, we can say. Here we use additional pointers to every node, which is a reference to the node above the particular node. So this is a structure of the particular this our approach. So this int key and int object is basically obvious, and left and right pointers also obvious. But here this additional pointers are r left and r right. This r left and r right is a reference to the parent of the particular node. Sometimes we use here only parent as the additional information, but here I have written r left and r right. So and in this approach we need additional memory. It is not problem, because now in growing technology memory is now large, but the problem is that when we put operations like insertion, deletion, and any other rotations, so that at that time we need to change these pointers, additional back pointers, which sometimes leads to errors in programming. So this is the back pointer approach. So now let's see the third approach, which is back pointer with lazy update. So this is the extension of our previous approach, which is back pointer. So in this approach, the structure is the same. We take additional information in every node, but the one change in this approach is that we don't need to change our this back pointer when we doing operations like insertion, rotations, etc. But we change this pointer only during the traversing from root to leaf, like we are when we are searching, etc. operation. So this is the back pointer with lazy update. We lazily, we can say, update the pointers of our particular node. So this is the third approach. So now let's say our fourth approach, which is reversing the path approach. So in this approach, we have removed the problem of extra stage in our previous approaches. So basically, what is this approach? So from the name, we can say that in this approach we are reversing the path. Mean we are reversing the path direction of our pointers. So if we go down in our tree, and we if we traversing from left direction, then we put this left pointer as a back pointer, and we change the direction of that particular pointer. And if we go from right, then we put this right pointer as a back pointer and change its direction. So here shown is an example of this diagram. to R to L, we change this direction of the particular pointer. So when we reach the leaf, how we decide that the left pointer is a back pointer or right pointer is back pointer? So this is the condition for the same, that if our left pointer data is greater than our particular node, so which is violating the condition of our BST, so we can say that that particular pointer is our back pointer, and if right pointer data is greater than our particular node data, then we can say that this is our back pointer. So these are our four approaches of returning from leaf to root. So if you like this video, then please share with others and subscribe our channel.